Thanks everyone for coming here via Zoom to attend Yaqing Wang's PhD dissertation defense plus his GBO. So it's my great pleasure to introduce Yaqing, his PhD student from my lab. He first came here as an undergraduate for a year to work as an intern, and I was very impressed by his performance, so I included him as a PhD student. Ever since I first got to know him, Yaqing has struck me as being very earnest, really ready to learn. And over the last 6 years or so, he has really demonstrated his great creativity and a very impressive ability to learn from across many disciplines and then integrate all these into his research. Also, he has really struck, as I mentioned, as being very earnest, that he take a great initiative to help others in the lab, and also to help manage the lab. He's the most senior student who sits in the faculty space of our lab, and has managed that space very well. So he has also mentored many students, a lot of undergraduate and master students, and given them a lot of guidance, greatly helped me exploring a lot of new directions in the laboratory. So a lot of these researches that he has helped lead exploring has led to great contributions to new projects, which even led to grant proposals. Yeah, so overall, I have been super impressed with Yaqing. Recently, he secured a postdoc position to work with Professor Simon Swanberg at Georgia Tech, one of the leaders in studying the biological aspects of neuromechanics. Yeah, so let's hope Yaqing has a successful defense and can move on to his next step.
Thank you. Okay. Thank you for the introduction. And welcome everybody. I'm Yaqing. My defense topic is biological and robotic studies towards intelligent global physical interaction with complex terrain. We know that the animals are amazingly good at traversing complex terrain. They do this by physically interact with the terrain and condition between various locomotor modes. On the other hand, even the most advanced robots struggle to physically interact with the terrain because we lack an understanding of the physical principles of such interaction. So let me briefly recover the previous research of electric locomotion using the interdisciplinary approach at the interface of biology, robotics, and physics. To move on a modest terrain like a paved road, animals usually run or walk. Animals usually run or walk. Study on this revealed these basic models like the three-mass model and the inverted model as the simplest model, as we call template for running and walking. And based on this understanding, many advanced robotic runners and walkers were created. To navigate in a terrain where there are sparse obstacles like sparse forest or the street, the animals know to avoid the obstacles while navigating. Similar to this, the artificial potential field help the robot to navigate this terrain by obstacle avoidance. To navigate in this terrain with thin obstacles, such as the dense forest floor, the animals physically interact with the obstacles. However, we lack these conceptual models for this physical interaction, which result in that even the most advanced robots fail to effectively interact with this terrain, which handle many critical applications, such as this search and rescue in earthquake rubble. So to remedy this, over the last decade, our lab tried to discover the physical principles of such interaction in the diverse terrain using a model organism of a destroyed cockroach. This cockroach is naturally well in the rainforest of the Central America, where they encounter with various kinds of obstacles every day. To negotiate with them, they physically interact with them and use multiple locomotor modes and open transition between them. So to understand how this locomotor transition emerged from physical interaction with the obstacle, we studied this animal traverse these obstacles like a bump, a gap, a pillar, a grass-like beam, and also self-rising. And based on the animal observation and the robotic model, we summarize the stereotype locomotor mode and the transition pathway of each challenge. And then we propose this potential energy landscape model that describe and predict these locomotor modes and conditions that I will further explain later. And based on this understanding and the animal inspiration, we come up with straightforward control strategies that enable the robot to have better performance. So similar to the artificial potential field serve as the foundation of most robotic navigation to achieve this obstacle avoidance. We think that this the potential landscape model began to serve as this fundamental principle to the physical interaction with the terrain. To elaborate on the potential energy landscape idea, I want to use the model system of the and robot versus obstacle. This is also the model system that I use in all my PhD work. So to beam obstacle, if the beam is really flimsy, the animal can just use this what we call the pitch mode. In this pitch mode, the animal just run to the beam and push down the beam to run through. However, when the beam is a little stiff, the animal cannot push through. Instead, it transitions to this what we call the roll mode. When this roll mode, the animal rolls its body and maneuvers through the gap. Oh, hello. Hello, thank you. Yeah, maneuvers through the gap. So this is a typical trajectory of the coupler in the space as a function of body roll and body pitch. So initially, when the animal runs into the obstacle, it stays in this horizontal posture of when it hits the beams, it picks up its body due to the resistance from the beam. And then it rolls into the gap. So it rolls decreases and pitch decreases, and finally to the roll mode. And after it resumes back to this zero pitch horizontal posture. To understand how this locomotor transition emerged from physical interaction with the beam, we come up with this simplest model where the body was modeled as rigid ellipsoid and the beam were modeled as the bendable bendable beam plate with torsional springs at the bottom. So the potential energy of the whole system is the gravitational potential from the body and the elastic potential from the beam. To use this, we can calculate the potential of the whole system when the body is near the beam region. So here is the potential as a function of the body's roll and pitch angles when the body is in the middle of the beam. You can see that there are three local minimum basins here. In the middle, this is the pitch basin correspond to the body pitch up. On two sides are correspond to the body roll into gap. So the local transition from the pitch mode to the roll mode is this like escape from this pitch basin to reach to this roll basin, which one cross this transition area. So on the potential landscape, the stereotype locomotor modes are attached basins on it, and the conditions between locomotor modes are destabilizing the ones on the landscape. I should also inform you that for this reversal, this landscape evolves as the body moves forward. So initially, when the body there's because the potential energy all comes from this gravitational potential energy of the body, it has a global minimum of 0.0. As the body moves forward and hit the beam, this global minimum evolves into this pitch basin, while these two other roll basins emerge. The body can still keep this pitch basin stay in this pitch mode, or it can go to this roll mode. And finally, when the body moves away from the beam, this potential energy landscape reduced to its initial condition. So in the animal experiment, we have kinetic energy fluctuation from body oscillation and induce this condition without central feedback. To test this, we put this straightforward robot model. I'm sorry for mic. Or is this okay? Let me try more. Yes, we come up with this. We build this straightforward roll physical model, and this model can just do free pick and roll without control. This model was propelled forward without any sensory feedback. Oh, thank you. Yeah, it can propel forward without any sensory feedback, and also it can like oscillate vertically to generate this kinematic energy fluctuation. So our robotic experiment proved our hypothesis that without this oscillation, the robot will stay in this peak mode because without oscillation, there's no enough potential energy accumulated, and the robot cannot transition to this flow mode by passing this barrier. On the other hand, if the robot is oscillated, it can transition to the flow mode immediately because with this oscillation, there's enough potential energy accumulated from this kinetic energy fluctuation that enables this transition. So this also tells you that this potential energy landscape model also describe and predict the robotic experiment similar to the animal. So so here this is the end of the introduction to previous work, and my story begins here. Yes. So let me briefly capture the knowledge gap of this potential energy model that I want to contribute to. So first, in the biology, we found that in the animal experiment, that the biology transition happens before the transition barrier is lower than the kinetic energy level. That means that the kinetic energy fluctuation alone cannot help to accumulate enough potential energy to transition to another mode. We all know that the animal use both sensory feedback and mechanical feedback to modulate its locomotion. And in the animal experiment, we see that the animal make a lot of adjustments on its head, leg, and abdomen. So we hypothesize that the cockroaches adjust its body and appendages through sensory feedback to do this transition. And we want to use this powerful tool of the potential energy landscape to understand how this biological adjustment facilitates this transition. In the robotics, unlike this robot can use visual sensing to scan a geometric map of the environment where they can apply this artificial potential field on, we lack understanding of how to apply this potential energy landscape in an unknown environment. Also, even we have this potential energy landscape, we don't know how to use it to get feedback control of the robot to physically interact with the terrain. So there are the summary of the three knowledge gaps that I want to contribute on in my three program. So in the first program, I want to cover the usefulness of animal adjustment using the potential energy landscape. We answer how to quantify this adjustment and whether the adjustment can facilitate the condition in an energy perspective. In the second project, we want to obtain the potential energy landscape in an unknown obstacle. We want to answer how to take this force sensing and how to use it to obtain the potential energy landscape. On this third project, we want to use the potential energy landscape to guide the robot to make transitions with least effort. We want to answer what the least effort conditions are and how the potential energy modeling can inspire this control to make such a transition. Let me first go to the first project of understanding the biological adjustments. All right. Yes. So you can see that when the cockroach traverses this spin obstacle, it can make a lot of this adjustment on its head, abdomen, and legs. To quantify this adjustment, we did the experiment again. And this time we have markers on the animal, especially those tails on the animal thorax and head, and the bit on its hind leg, and this white out on its abdomen. So we can track these markers to get accurate kinetics of the cockroach. Based on this quantification, we highlight two observed adjustments. One is the leg tucking in. We quantify this leg tucking in using the angle between the two legs. Statistically, the animal tucking its leg more when it's rolled than it's running or pitching against the beam. Another adjustment is the frequent head oscillation. We quantify this head oscillation using the angle between using the standard deviation of this angle between the animal's head and thorax. Statistically, the animal oscillates its head more when it's negotiating with the beam than it's currently running. To understand the usefulness of this adjustment, we first want to quantify what is the difficulty of such a transition. So this is the potential energy landscape. You can easily spot the peak minimum, rho minimum, and the saddle point on it. So this is actually showing you the approximation of this peak and rho minimum. So the transition barrier is defined as the energy difference between the peak minimum and the barrier. To involve this leg and head adjustment in the system, we further augmented this animal model to more detailed and added head and legs on it. And we systematically vary this head sprawling angle and this head angle to see how they affect the energy landscape and the transition barrier. So here are the results. This is the transition barrier changes as the leg sprawl angle reduces. You can see that when the leg sprawl angle reduces, this transition barrier reduces, especially at the place where the angle position. You can see that the leg sprawl angle reduces can reduce the barrier by 35 times the average kinetic energy fluctuation, which means that leg tapping in significantly reduce the transition barrier.
Just to clarify that, Jane, you're saying you're taking the measured kinematics and playing them through the numerical model to evaluate the effects on the energy landscape?
Yes.
Okay.
Yes.
So every, I guess, what are the different level sets, the different
Yeah, they are the different leg angles. So you cannot force the animal to do this, so you can only calculate it in the model. And this one is the top ones are like the very widely spread, and the bottom one are the tucking in.
and those are all within the biological range that you measured?
Yes. This is a little over the biological range that we observe. Yes. So for the head oscillation, you can see that the transition barrier does not change back as the head angle changes, especially at this transition when the transition happens. This oscillation change can only reduce the barrier by 57% of the average kinetic energy fluctuation, which means that the head oscillation does not significantly reduce the transition barrier. So we hypothesize that this instead this head oscillation is a form of active sensing. I can explain it more in the question section. So this is the end of my presentation. To recall another knowledge gap of that we cannot measure in non-annual terrain. We hypothesize that we can use the force to achieve this, because the potential energy landscape emerges by the physical interaction between the robot angle with the terrain. So this physical interaction should be captured by this force sensing. So this is my second project to reconstruct this potential energy landscape in a non-known terrain. So in a frictionless for the case, the gradient of the potential energy landscape should be the contact force and the resulting force after considering the effect. When physically interacting with the obstacles, the robot should be able to measure this contact force. It can also measure to get the force angle, and the quantification of force angle force will also take the force. So this tells you that the robot can measure this force and contact position to the landscape. There are many existing robotic sensors that can measure this contact force and position, and even the even the resulting torque. For example, this commercial force sensor, this flexible sensory array, and this robotic antennae and wings. However, we think that they are not suitable for the four-legged robot because these commercial multi-axis force sensors are expensive, bulky, and pricey. This flexible sensor can only give you the normal force, and its signal has a free behavior that's difficult to analyze. These robotic antennae and instruments have large deformation. So we want to develop new sensors on a small robot to sense the force and contact. So this is what we do. We upgraded this old robot by equipping it with the capability of force and torque sensing. But this robot is cropped from the original robot as with a transparent green shape. We only keep this region where this physical contact occurs. to measure the contact force with each beam, we have two force sensors embedded. These two force sensors are custom. To measure the contact position with each beam, we cover the surface with contact sensors. So we want to use this robot to reconstruct a potential energy landscape in a very small region in this like white rectangular region on this landscape. To do this, we want the robot to systematically sweep this row and pitch state space for row from 0 to 40 degrees and pitch from 10 to 40 degrees, which already resulted in like 300 files. In each file, the robot was fixed in the row and pitch direction and is propelled forward to physically interact with the beam while sensing contact force. So actually, each file is a floating point on this landscape. This is a sensing result from a representative file. This is the measured force in the graph, the lateral and vertical direction, and the torque in the row, pitch, and yaw direction. If you compare it with the landscape gradient, you can see that it's roughly matched, which means that contact force and torque is the landscape gradient. We want to reconstruct the landscape using this graph force and the row and pitch torque. So here's the comparison between the landscape reconstructed and the ground truth. Just to say again that we just reconstruct a small region of the landscape in this white rectangular region. So every of these curve I showed you previously is a floating point on this measured landscape. You can see that this measured landscape captures this state of the ground truth quite well, which means that we can use the force and torque sensing to reconstruct the potential energy landscape. So this is the end of my second chart. Actually, the math behind it is default decomposition. I can elaborate on this in the question section. Although we can obtain this potential energy landscape using force and torque sensing, we still don't know how to use it to guide the robot to do physical work control to physically interact with the terrain. This leads to my third project to use the potential energy landscape in an algorithm that guides the robot to control its locomotion. So to come up with this algorithm, we first want to quantify like what or answer what is the least effort condition. So we claim that following a gradient extremal, especially the gradient minimal curve, is giving this minimal effort condition. This gradient minimal curve is a curve that on this curve it always follow its extremal gradient. For example, the minimal gradient or the maximum gradient. So especially in the gradient extremal curve across the saddle point, the gradient maximal curve is the barrier, and the gradient minimal curve links the saddle point with the local minimum. So our rationale is from the previous study, we know that the gradient is probably the resistive force and work. So if the gradient is minimal, the resistance should be minimal. And we also have some evidence in the biological observation that I can explain in the question section. Question is, how can the robot know the gradient minimal direction? So from the animal experiment, we can see that the animal always wedges the beam gap around its head against the beam, simply looking for a minimum resistance distance. So similarly, we found a way to obtain this continuous, to obtain this gradient minimal direction from the continuous force and torque sensing. I can show you the math details in the question section. But this is only accurate when it's a one saddle point. So this is how we find this direction. Once we find this direction, we will follow and convert it to this gradient minimal curve. So the robot should, after each stage, the robot should use the force and torque sensing to get this gradient minimal direction, as we call the climb direction, and also the vertical direction and the converge direction. So it should do this gradient ascent in this climb direction and do this gradient descent in the converge direction. It's just climbing the mountain. The path is the gradient minimal curve. You should climb along this curve while converge into this curve to climb a mountain. So we propose to have this approach for us to steer the system to do this. So the G's are the landscape gradient, and W's are just weight. This plus and minus sign here shows you the direction of gradient ascent and the gradient descent. And recall that there's a flaw that this gradient minimal direction can only be detected near the saddle point. But what if the robot is far away from the saddle point? So we first want to answer this question by quantifying whether the robot is close enough to the saddle point. So this is a potential energy landscape top view. You can see that there are the minima and the saddle point on it. And this is the identifier neighboring area of this like critical point. These blue regions are the neighboring area near the minimum, and the orange, actually yellow here, are the regions close to the saddle point. So when all of these can also be obtained from the continuous force and torque sensing. So when the robot is in the saddle neighborhood, it should generate this force to follow this gradient minimal. If it's in the minimum neighborhood, we want the robot to first go to the saddle neighborhood. To do this, the robot should generate this oscillation force, which is just like pure noise. And this is how the robot can continuously follow this gradient minimal curve. But there's another question remains, like why the robot knows that it should transition? What motivates it? To answer this question, we first look closely into this animal and see what motivates the animal transition. So initially, the animal pushes against the beam and tries to push through, actually trying this pitch mode, and it can be a good mode if the beam is flimsy. However, when the animal tries a lot, but cannot push through, it loses its patience and begins to oscillate and search for new opportunity. And when it suddenly finds this role mode, it quickly transitions to this role mode and traverse. So this tells us that this long-time entrapment in my mode may motivate this searching and transition to another. So all of this inspired this algorithm flow that enable the robot to do this transition. So when this transition only triggered when the robot has stayed in one mode and did not successfully traverse for too long. When it's near the saddle point, it applies this approach force to follow this gradient minimal curve. When it's in the basin, it do this active oscillation to go to the saddle region. And there's another part of this to make up the whole story, that sometimes this robot cannot know whether it's near the saddle or near the basin or near the minimum. So in this case, the robot should apply a sideways force to recover this detectability. I should explain this in the question section. So we apply to verify this algorithm, we apply it in the simulated robot using the chrono simulation. In this simulation, this robot can only sense contact force and torque, and the algorithm control are directly applied into this roll and pitch force. You can see that the robot can transition from this pitch to roll mode and traverse this beam just like the animals. I will show you the trajectory of the robot and the applied torque that corresponds on the potential energy landscape. The cyan and green and magenta arrows to be the approach torque, oscillation torque, and the sideways torque. Yes, they are in quantum classical. And if you cannot catch them, it's fine because it's also summarized in the next slide. Okay, using this algorithm, the simulated robot achieves 100% traversal rate. This is the trajectory of that robot. This blue, orange, and red curve are the trajectory near the pitch minimum, near the saddle, and near the roll minimum. And these cyan arrows are the approach force, which guide the robot to follow this gradient extremal direction. These green arrows are the oscillation torque, which enlarge the searching area in the pitch basin. And these magenta arrows are the sideways torque, which are solidly triggered. So all of them show you that the function of the control torque match our purpose. So we answered this question, how to use the potential energy landscape by proposing a new control algorithm that uses to guide the robot to physically interact with the terrain. And that's the end of my third project. So in conclusion, my project furthered our understanding of potential energy landscape in three aspects. It helped to use the potential energy landscape to understand the biological adjustment. We know how to obtain this potential energy landscape in an unknown environment, and it used the potential energy landscape to guide the robot to transition with this effort. All of these achievements further improve our understanding of this potential energy landscape and advance our understanding in how the animals and robots will physically interact with the obstacle. As you can already see that we are adapting this interdisciplinary approach at the interface of biology, robotics, and physics in our study. And I also want to propose future directions in these three directions. In biology, we propose to use neural tools to examine whether the claimed adjustments are from feedback or just passive. A brilliant example is from a study of a cockroach for this rough terrain. They measured the muscle action potential of the cockroach running on a flat terrain or on the rough terrain. You can see that they are quite the same. Then this measurement serves as a direct evidence of the absence of the neural feedback here. Actually, we can do similar research to measure the to verify if the claimed adjustments are actively generated or not. A second is to understand the biological sensor fusion. So a good example is a study shows that mouse use both vision and mechanical sensing to detect the flower. When the cockroach traverses spin obstacles, it can sense the force of torque from the sensors like Hamilton and cilia, but it also uses vision and antennae to sense. And we want to know how to fuse this vision and contact-based sensory signal to generate this geometry and force torque information. In robotics, we develop sensors for real-world terrain. I think we can use an inspired sensor design from this salient cluster on the insect skeleton. There are just biological membranes on the skeleton. When the skeleton deformed by the external force, they also deform. And they are grouping many and have various orientation, and this allows it to provide force along multiple directions and also be robust against damage. We think that we can mimic it to achieve the 3D force sensing on the robot surface. Another way is to use this neural network estimator to estimate the least effort transition direction. So example is a project that studies how the fly knows the absolute wind angle from its sense the wind angle and kinematic. In a neural network estimator, they put the sense wind angle and its kinematic as the input and the absolute wind angle as the output. We think that we can do a similar job to place this input with metric force and torque and kinematic of the robot to get the least effort transition direction. And this will make the math calculation of this direction much easier, which facilitate the application in real world other than simulation. The way is to test this algorithm using a free running legged robot. So a free running legged robot, unlike the pedal robot we use, it faces more challenges, such as the need to process noisy sensory data, deal with high-dimensional motion, and generate effective propulsion. We think that we should overcome all of these challenges to finally bring our algorithm into real-world application. In physics or modeling, we propose to use the Longevin equation to capture the full dynamics of the physical interaction between locomotion and terrain. This is the equation, Longevin equation. The Longevin equation not only captures the potential energy landscape part, but also capture the damping and also the randomness in the system. This is a probability distribution of the robot trajectory in my simulation as the time evolved in a peak and roll cross section. You can see that it's already showing up this stochastic diffusing nature of the physical interaction system, which can be better captured by the Langevin equation. And based on this Langevin equation idea, we propose to use data-driven method to obtain the potential energy landscape in unknown environment. We propose to release animals and people were control robots into the terrain and physically interact with them and use the classical statistical data-driven method or machine learning-based approaches to fix this potential energy landscape gradient term in the Langevin equation to get this landscape. So that's all of my presentation. With all this, I will thank my advisor, Dr. Kendi, the dissertation reader, Professor Cohen, and reference, my GPO committee and alternative, our funding sources, my co-authors, the people offered insightful discussions and help professor and their group help my postdoc application, the ME and LCR staff, my lab colleague, my other friends in Baltimore, and my family. Thank you, and I can take questions.
Thank